In the previous example, you explored how the data can be interpreted and a linear function can be made to pattern that data using 2 points that are given. However, as you've seen, the predictability about how well it works and the equations that you would get could vary significantly depending on the pair of points you chose. So another way of handling it is to use more of a statistical way of doing it, and that's using regression. Now, most of the regression you're going to be asked to do, and this is why it doesn't usually end up fully on a final exam, is that you're going to be using your graphing calculator to do a lot of it, because the individual calculations to perform a linear regression can be tedious, and that's something that is studied more in a statistics course than it is in a college algebra course. So a lot of this is going to show you how to make use of the calculator to do this. So this demonstration, we're again going to explore this public college data. Again, we're going to use the fact that Y is the cost and X is the number of years in 1985, so these will be adjusted accordingly as they were in the previous demonstration and example 5. And so you want to come up with an equation for the best fit regression line for the data. That best fit regression line may not pass through any one of these points. Basically, a best fit regression line, well, it's basically minimizing the overall distance from all the points, rather than just picking a few of them and saying, I want to be close to these ones, but even if these other ones are far away from it. So how do you do that? So let's pull up my virtual calculator here, and I'm going to show the screen. One of the first things you're going to have to do is get this data that's over here, and you want to put it into a table in your calculator. So what you want to do is hit the Stat menu, and you want to go to the first choice, which is Edit, and you get a tables like this. Now, as you see, I've already pre-filled these with the entire table. L1 is my values from 0 to 22. L2 is the public school costs, and L3 is the private school costs. So I've taken all the time to enter this in. You basically enter this in like a spreadsheet. So it's just, that's tedious work I didn't want to show for the video. So you would spend some time to get this data entered in. If you enter it all in, just be aware of what is where. So the year is in L1, the public is L2, the private's in L3. For my setup here. And what I want to do now is, well, one of the things I could do, once I have all that data in, I set up my graph to kind of go with the scaling we saw in the previous graph. So it's going by 5s for the X's, going by 5-year increments. It's going by 5,000s for the Y's. And so that I have a graphing region that's very similar. It's not going to show the numbers, mind you, but it's very similar, so that I can verify that what I'm seeing here, as well as a scatter plot I'm about to make, is in line with the data and the previous graph. So I could do that by going to Stat Plot. I'm going to go to the first plot. And again, I've done some of this ahead of time. I'm just going to turn this on. The first choice is a scatter plot. I want my X list, which is the year L1. That's where they were. My Y list for public school costs was L2. I usually choose this first mark because it's the one that's easiest to see on a TI-84 screen. And because I have a newer version shown here, I can actually change the color, which is good. You may not have that option if you have an older version of a TI-84. And now if I hit graph, you can see the scatter plot, which looks a lot like the scatter plot you saw for the public school data beforehand. Now what I want to do is I want to come up with a line of best fit that fits this data as best as possible. Not the one that we had that like fit this much and was falling off here, or not the one that was going to here and falling off at the end. I want it to fit the data as best as possible. So now I'm going to go to Stats. With the data entered in, I'm going to go over to Calc, and I'm going to go to Linear Regression, which is choice 4. I want to put in my X list, which is again my years, that's L1, my Y list is L2. I don't have a frequency list. Storing regression equation, I'm going to actually put something here. I'm going to go to the variables button, which is the VARS button down here. I'm going to go to y variables. We work only with functions really in this course, so it's the first choice. And I'm going to choose y1, which if you notice, when you go to the graphing region, I'm just going to show before I do that. If I go to where I would enter in graphs and whatnot, y1 and all these other things are what you would see here. So these coincide with these variables here that you could eventually graph on a graphing table. So I'm going to store here. I'm going to go to variables, choose the function, choose y1, and that's going to put the equation, which can sometimes have really nasty looking decimals in it, and copy it over for me. And I'm going to hit calculate. Now, one of the things I wanted you to keep in mind is if you don't see this r squared and r value showing up, you may need to go to your calculator and change another setting and turn diagnostics on. So let me go through that briefly. Diagnostics is not really easily accessible by any combinations of keystrokes you do up here. So I'm going to go to the catalog, which is down here above 0, of all the commands in the calculator. So all the commands in the calculator are cataloged here. You can actually get them from here. I'm actually going to hit the x to the -1 power button. I don't have to hit the alpha, but notice that D is there. If I hit this, it's going to go down to the D's. And I want to come down to diagnostic on. And just hit enter. And now, if you go back and run that calculation again, once you have it turned on, it should stay on for the rest of it. I don't have to store the regression equation again. You should get the r values, but it's telling you that y equals ax plus b. A is the slope. You have the 140.3478261. It's rounding off the decimals here. You have 804.6521739 here. But you can also notice, if I come here, it's been stored here. It has far more decimal places there too. So there's more decimal places in the memory at times than are sometimes being shown to you. And if I were to graph that, you should see it fits pretty nicely. It's not too far away from any one of these points. It seems to be passing through a number of them, but it's not very far away from any one particular point. So this is the line of best fit. So getting back to here, I got an equation that fits this. Now I wrote the number of decimal places that came up in that first thing, but how well does the regression line fit the data? Well, previously we had issues with the predictions we made in the previous situation. Here, the line did more along the lines of this. So it fits much, much, much better. But another measure of how well it fits is this R value, which we saw was 0.9768, so forth and so on. It's on your calculator as R, and a lot of textbooks will call it R. Your book calls it CC. It's for the correlation coefficient. And basically, the correlation coefficient is a measure of how close to linear the data is fitting and how well this regression line fits that data. And basically, the way it works is 0 represents no relationship. These correlation coefficients have a relationship with the slope. They're not the slope themselves, but they are related to the slope, and the calculation is related to the slope. But essentially, if you have a +1 or a -1, that's perfectly linear. That means that these are lining up, and if you actually went through and did your rates of change throughout, you should have a constant rate of change. So basically, the closer it is to +1 and the closer it is to -1, the better the relationship. The smaller it gets and closer to 0, the worse it is. So with this being a 0.9768, that's a pretty good fit. That means that this is a strong correlation, and as a result, we would say that this is a good prediction. So this is showing a strong positive correlation because this correlation coefficient is close to 1. That means that we can make a prediction using this formula. Again, I'm going to use x equals 37. Now here's the other advantage of using the calculator and storing it. Getting back to the calculator, showing the screen here. So I have this equation stored in here. Now what I can do, if I want to figure out what goes on at 37, instead of having to do a lot of typing and put a lot of decimals in, and the fact that it's stored in the calculator under y1, if I go to the variables again on my regular screen and choose y1, all I have to do is put the parentheses in 37. That says that I'm going to go to that equation in y1, substitute 37 in for x. It's basically function notation. And so that would be the prediction, $5,197.52, which is what that is. And so that would be your prediction, which you see is between the other two values. So as mentioned in the previous one, that is a better prediction because it fits the regression line, which is the best fit for that data. Now you're going to be asked to do the same thing with the private school data. So be sure to do that and then check your answers afterwards.